The concept of the fourth dimension has long been a playground for mathematicians, philosophers, and science fiction writers. But the emergence of artificial intelligence has transformed this abstract realm into a tangible frontier of research and creativity. AI is not merely a tool for visualizing higher-dimensional spaces. It is becoming an active partner in exploring, generating, and even inhabiting these dimensions. From generating dynamic 4D scenes from a single image to simulating how a four-dimensional creature might perceive its world, AI is pushing the boundaries of what we can see and understand. One of the most significant applications of AI in this domain is the generation of 4D content, objects and scenes that exist in three spatial dimensions and evolve over time, which is often considered the fourth dimension in computer graphics. This is a monumental leap from traditional 3D modeling, as it requires the AI to maintain both spatial and temporal coherence. Recent research has demonstrated remarkable progress in this area. For instance, the framework Helix 4D can generate complex 4D meshes from input video, tackling challenging scenarios like topology changes, deformation, shattering, and even melting. It achieves this through a sophisticated pipeline that includes sparse-structure, geometry, and material generation stages, employing sliding window cross-frame attention to share information across frames and a clever encoding technique that repurposes low-frequency spatial positional bands for temporal encoding. This allows the model to understand not just the shape of an object at a single moment, but how it transforms and interacts over time. Similarly, the DimensionX framework takes a different approach, generating photorealistic 3D and 4D scenes from just a single image using video diffusion models. The core insight is that both the spatial structure of a 3D scene and the temporal evolution of a 4D scene can be effectively represented through sequences of video frames. To overcome the limitations of traditional video diffusion models in recovering 3D and 4D scenes, DimensionX introduces ST-Director, which decouples spatial and temporal factors in video diffusion. This decoupling allows for precise manipulation of spatial structures and temporal dynamics, enabling the reconstruction of both 3D and 4D representations from sequential frames. The system also incorporates a trajectory-aware mechanism for 3D generation and an identity-preserving denoising strategy for 4D generation, ensuring that objects maintain their identity as they move and change over time. The CAT4D method offers another perspective, leveraging a multi-view video diffusion model trained on a diverse combination of datasets to enable novel view synthesis at any specified camera poses and timestamps. This model can transform a single monocular video into a multi-view video, enabling robust 4D reconstruction via optimization of a deformable 3D Gaussian representation. The implications for virtual reality, filmmaking, and interactive media are profound, as it allows for the creation of dynamic, immersive environments from very limited input data. These advancements are not limited to objects. Researchers are also developing techniques to generate panoramic 4D scenes at 4K resolution, as demonstrated by the 4K 4DGen framework, which elevates a single panorama to an immersive 4D experience with 360-degree views. Beyond creating 4D content, AI is also being used to visualize the fourth dimension in ways that challenge our very perception of what a higher-dimensional being might see. A fascinating project called 4D volumetric retina simulation tackles the question of how a four-dimensional creature would perceive its world. Most visualizations of 4D space present wireframe models or simple 3D cross-sections. However, this simulation argues that a 4D creature would possess a 3D volumetric retina, analogous to how we have a 2D retina. The project implements a physically based 4D path tracing engine to model light interaction in a 4D scene, simulating image formation onto a defined 3D volumetric retina. It then introduces an acuity model, assuming sensitivity is highest at the center of the 3D retina and falls off towards the periphery, similar to foveal vision in humans. By combining multiple 2D slices from this simulated 3D retina, weighted by the acuity model, it produces a composite 2D image that offers a richer, more nuanced representation of 4D visual perception than previously available. This is not just about creating a cool image. It's about building a conceptual model of what it would actually mean to perceive in 4 dimensions. AI is also being used to explore the 4th dimension mathematically, offering new ways to visualize and understand complex, high-dimensional data. The visualization of multidimensional point clouds as a swarm of avatars uses AI to map high-dimensional data onto a 3D space, with avatars that encode data dimensions through visual features like color, size, and shape. This technique, which builds on the concept of Chernoff faces, allows users to intuitively explore complex datasets by leveraging the human ability to interpret facial traits. In a related application, the RF-FATE tool, which stands for Random Forest Potential of Heat Diffusion for Affinity-Based Trajectory Embedding, is a supervised data visualization method that enables exploration of relevant data relationships in multidimensional biological datasets. It has been used to identify previously suspected subtypes of multiple sclerosis by preserving the structure of how data groups relate to each other, addressing a key weakness of other methods that tend to overemphasize differences between groups. In the field of time series classification, AI researchers have integrated hyperdimensional computing, HDC, into methods like Mini-Rocket and Hydra to explicitly incorporate temporal order, which is a form of 4th-dimensional structure, time being the 4th dimension. Traditional methods aggregate features over time in an order-invariant way, missing longer-term sequential patterns. By using HDC to bind feature encodings with encodings representing temporal order, the new method can discriminate time series based on structure, achieving a relative error rate reduction of over 50% on several datasets. This demonstrates that the framework of higher dimensions is not just about abstract geometry, but is a powerful tool for interpreting data. The future of AI in visualizing and exploring the 4th dimension is rich with possibilities. As AI models continue to advance, we can expect even more sophisticated methods for generating, simulating, and understanding higher dimensional spaces. The gap between abstract mathematical concepts and tangible, interactive experiences is closing, inviting us to explore the boundaries of reality in ways that were once the sole domain of imagination. AI is not just helping us see the 4th dimension, it is teaching us how to think in it.